we discussed about conservation of linear momentum. So once we do that, we know that the rate of change of linear momentum is equal to net force on the system, and then we can write this conservation of linear momentum principle for the for our differential control volume, and for that differential control volume we can write that differential force, which is delta F, that is the product of differential mass of that control volume into acceleration. Right. So now in the last class we discussed that there are two types of forces. One is the first one is the body force, which is distributed throughout the element, and it depends on the volume of that object on which object or element on which the force is acting. So we know that body force we can calculate by the product of delta m into the gravitational acceleration. Right. So after that, the second type of force is the surface force, and in the surface force we have got two types of forces. One is normal stress, which is perpendicular to the surface at each point, and shear stress, and we require two shear stress on a plane. So they are perpendicular to each other. So you can see that delta F1 is the force which is producing shear stress in this direction, which is x direction, and then delta F2 is the force which is producing shear stress in the z direction. Right? If we take it like x by t, and then if we want to get the net force on the element, we need to first of all we need to consider. Okay, so this thing we did. We need to consider the forces. So first of all, we say that at the center of the volume, the forces are the stresses are sigma xx, tau xy, and tau xz, and then we can just calculate these stresses at the faces, different faces, and for that we use Taylor series. So if we use the Taylor series, we can get the normal stress at the right face and normal stress at the left face, and then we can add up, and then in the end the net force in the x direction, as we discussed in detail in the last class, that becomes equal to the last equation in this slide, and then similarly we can get the forces, net force, surface forces in the y and z direction. Once we get the surface forces, we know that the total force is the summation of surface force plus body force. So if you remember that in the last class, we came up with this relation for inviscid flow. The inviscid flow is the flow in which there is no shear stress. So it means that tau component would be equal to 0. And then the shear stress, normal stress component would be equal to minus P. So if we do that, we can say that the equation that comes out to be, that is Euler's equation. So we can see here on the left hand side, the first term is due to that body force rho into gx, because the volume, differential control volume, was appearing in each term, so we kind of cancel it out. So rho gx minus partial p by partial x into rho into, and this bit on the right hand side, that is the acceleration bit, that ax, ay, and ad. So we have got three equations in which we have got acceleration on the right hand side and the net forces on the left hand side. So after that, we discussed that for the inviscid flow, we can also take the assumption of irrotational flow, and the a practical application of irrotational flow is uniform flow in the x direction, like parallel flow. Yes, any question? Any question? Okay, maybe it will just. Okay,
No, sir.
okay. Thank you for confirming that. So we were talking about the application of in-visit uh, uniform flow. So that is the flow which we usually encountered in a flow where we have got uniform approach velocity, as in the figure shown. So if you see here that in the vicinity of this body on which the flow is happening, there are some kind of velocity gradient. So it means that we can no longer take it parallel flow in the vicinity of the solid surface. But if it is far away from that body, we can take it parallel flow. So we say that there is no shear stress in that region where we have got uniform approach velocity. And similarly, as I discussed in the last class, that we can also take this assumption in the entrance region of a pipe flow. So in pipe flow, there is an entrance region in which the velocity profile develops. So that in that region we can say that because the velocity is constant in the radial direction, so there is no shear stress. So in entrance region we can say that flow in channel, we can say that that is kind of a in entrance region it is a parallel flow. And once it is fully developed, we know that it becomes parabolic profile, and we will discuss it in detail that how to get this shape for the channel flow and pipe flow in chapter number 6 and chapter number 8 in detail. So please read. I think this is one page. So it was just a recap which we discussed up till now. And then the last slide we covered that if we have got incompressible Newtonian fluid, then the normal stress is that is equal to minus P plus 2 mu partial U by partial X. And similarly, for Y and Z, we can have these components. Now, there is a statement written in the end that where P is the pressure, the negative of the average of the three normal stresses. So how do we get it from here? So if I consider 2D, okay, let me write it here that if I have got sigma xx is equal to minus p plus 2 mu partial u by partial x, sigma yy is equal to minus p plus 2 mu into partial v by partial y, and partial vv is equal to minus p plus 2 mu partial w by partial z. So if we add them, we can say that here we would have sigma xx plus sigma yy plus sigma vv is equal to minus 3p plus 2 mu into partial u by partial x plus partial v by partial y plus partial w by partial z. Okay, so let me. Okay, can anyone tell me that what is this term, which is in this red rectangle? What is this term from the previous week lecture? If you look at your book or notes or anything, you can easily find that this is continuity equation, which comes from continuity equation, which comes from the conservation of mass, and we write it. But for the incompressible flow, we can write, for the incompressible steady flow, we can write partial z is equal to 0. So it means that this term becomes equal to 0. When it is equal to 0, then we can write that minus p is equal to 1 by 3 sigma xx plus sigma yy plus sigma zp. Right. So now we can see that how we have derived this fraction in terms of normal stresses. It is basically the average of the three stresses, and then the shear stress can also be written in terms of, because I understand that in chapter number 1, I think you must have studied a relation that which states that for simple uh, for a flow over a flat plate, if we want to know the shear stress, that is equal to tau is equal to partial du upon dy. So that is only for one dimensional flow. But here, because we are talking about three dimensional flow, then the shear stress would be kind of written in these terms. So mu into partial u upon partial y plus partial v by partial x, and then similarly tau x z is equal to mu into partial v by partial l plus partial w upon partial y. Okay, and now if we see that we have got these equations. Now if we want to put these relation of sigma xx tau xy in these equations, okay, just then we can get these equations. Okay, so now uh, coming from this point to this point, it needs a little bit of mathematical manipulation, which is not shown in your textbook. So let us do that. That how we can derive uh, this relation, like this x direction momentum equation from this governing equation in terms of stress. So let me first of all copy it, the first equation from here. Sorry, it should be copy, and then we can just paste it here. Okay, so this is our equation, and then there are certain terms on the we are going to talk about the left hand side, because if you see in the slide, the this bit, which is the acceleration bit, that is written unchanged here. The only change is on the by writing the relation for sigma xx, tau xy, and tau xz. So those relations are written here. Tau like tau xy and tau zx, they are written here, and similarly. So we can just write the relation here, and then we can put the values to see that how things are manipulated to get the final equation. So first of all, I would write what is sigma xx. Sigma xx is equal to minus p plus 2 mu into partial u by partial x, and then here I need tau yx, so tau yx would be equal to mu into partial u upon partial y plus partial v upon partial x. Similarly, tau zx would be equal to mu into partial w upon partial x, partial w upon partial x plus partial partial u upon partial z. If you see partial w upon partial x plus partial u upon partial z. Right. So let me partial u upon partial. Okay. So now if we only consider the left hand side of the equation, so I am going to rewrite it rho dx. Now I am going to put these values here. rho gx plus minus t plus 2 mu into partial u by partial x. Instead of sigma xx, I have put this value divided by partial x plus partial by partial y into mu into partial u by partial y plus partial v by partial z plus partial by partial z into mu into partial w by partial x plus partial e by partial u by partial z. Right. So now I am going to kind of do a little bit of mathematical manipulation. Just stay with me on this. So first of all, the first term would come like this: OGX plus, and now it should be minus partial p by partial x, the first term here, and then because this is 2 mu partial u by partial x, so I can write it mu into partial u by partial x plus mu into partial u by partial x. So that's what I am going to do. That first of all, I would write partial by partial x into mu into partial u by partial x. So the other mu I would write somewhere here. Let me write it here separately. So that would be equal to partial by partial x into mu into partial u by partial x. So okay, so let me take this mu out of this. Okay, let me write it again, maybe better way. So it would be partial by partial x mu into partial u by partial x. So the first term I have written like this. So this term here mu into we would simplify it further in the next step. The second term here I am going to write, that is partial by partial y mu into partial u by partial y, and then this term here, if you see that here it would be, I think it should be partial u by partial. Here it should be partial u by partial x. Okay, so now we can change the order of differentiation, because we know that differentiation has a commutative property. So we can take partial by partial x here, and we can just write partial. We can commute this partial x with partial y. So if we take partial x common, so what would be here? Partial v by partial y. The second term, I am talking about this term. So this term with this term, because there is partial y here and partial x is there. So if I take partial x here and when I multiply it with this, so I can commute these two differentials. So partial x would come out and partial y would come, partial v would go under this. So partial v by partial y, I have written this, and partial by partial x, that was common here. So I hope that you are understanding this point. And then similarly here, that here as well, you see that we have got partial w by partial x. So, and the third term here would be partial by partial z mu into partial u by partial z. And then if you again look at this, we have got partial z and partial x. So we are going to commute it. Commute means that partial x would come here and partial z would come there. So if that happens, then partial by partial x would be common, and then here I can write partial w by partial z. Right. Now again, if you see that this is the continuity equation for incompressible static flow, so we can just make it equal to 0. So now we are left with rho dx minus partial p by partial x plus mu into partial k u upon partial x square plus mu into partial k u upon partial y square plus mu into partial k u upon partial z. So now if you see on the slide, we have got a similar kind of relation that mu into partial that once we put the stress values, then we can write x direction Navier-Stokes equation in the x direction, that is mu to partial scale u partial x square plus partial scale u upon partial y square plus partial scale u upon partial z square. Now, once we have derived this equation, we know that this is a non-linear second order, because we have got second differential term here, partial differential equation. One thing you would be quite worrying at this point, that how to memorize all these relations. So I am going to tell you a very simplistic way to kind of remember only one equation, and from there we can derive all these equations automatically. So let me tell you about that method. We call it tensor notation. In tensor notation, we have got two types of indexes. One is called free index. Free index means that that value can be I1 from 1 to 3. It depends upon that how many dimensions we are taking. And then the second one is called repeating index. Repeating index, and it is kind of repeating index, or we also call it dummy variable, dummy index, or bounded. So it tells us about the summation. So these equations which are written here, let me write this equation in one tensor form, and then I would explain that how to derive all these three equations from that tensor form. So I am writing that Navier-Stokes equation now in the tensor form. So the acceleration term is on the left. Okay, acceleration term is on the left hand side. So we can say that rho into partial ui. Now I am using that free index term here. Partial ui plus partial t plus, here I would write u j partial ui upon partial xj is equal to rho gi minus partial p upon partial xi plus mu into partial scale u of I divided by partial xj. Okay. Now this repeating index means that if in one term we have got the repetition of that variable, like if you see the first term, there is no repetition of variable, so I is a free index. But if you look at the second term, we can easily see that j is being repeated here. And then in the third term, I is again the free index. In the fourth term, which is the second term on the right hand side, I is again the free index. And then if you see the last term, then again it is j, it is repeated again, right? So now if I want to write the x momentum equation, so let's write it from here. X momentum linear x momentum equation if we want to write it from this tensor form. So we just put I is equal to 1. When we put I is equal to 1, then U1 is basically U, U2 is equal to V, and U3 is equal to W. Similarly, X1, that is X, X2 is equal to Y, and X3, that is equal to Z. So if we put I is equal to 1, just stay with me on this. Sorry, there is some lag. So if I write, so the first term would be rho into partial U1. Partial U1 is partial U, because I have written here partial U1 is U, partial D plus. Now because there is a repeating index, so it means that we need to take the summation. Summation means that from I is equal to 1 to j is equal to 1 to whatever dimension we are talking about. So because we are writing the equation for 3 decays, so j would start from 1 and it would go up till 3. So if I write u here, it would be u1. U1 is u. Then again I is 1, so that's why I am going to write u here, and then x1 is x. So partial x. Now, because there is a summation from j is equal to 1 to 3, so it means from this term we would have 3 terms. So the second term u2 is v. Then again I is equal to 1, because we are talking about x momentum equation, so that is partial u, and then x2 is y, so partial y. Then again the third term is j is equal to 3, that is w, and u3 is w, then again u1 is u, and then x3 is z. Now you can see that we have easily written this. The left hand side, the right hand side, I is equal to 1, so it would be gx minus partial p upon x1 is x plus mu into, now we need to write I is equal to 1, because there is again summation, so there would be 3 terms, partial square u upon partial x square, because when j is equal to 1, we can write x. Then again second term partial square u upon partial y square, because j is equal to 2 means x2 is y, and similarly partial square u upon partial z square. Right. So we have written this. Now if I say that if we want to write W momentum equation, so for W momentum equation, I would be equal to 3. W or V momentum equation. Then we put I is equal to 3. Again, rho into when U3 means W, partial W upon partial T plus, now there is summation. So here j is equal to 1, so u into, now I is equal to 3, so it would be partial W divided by partial x, right? Because x is equal to 1, then again when j is equal to 2, the velocity would be v, partial w by partial y. When j is equal to 3, then it would be w. When j is equal to 2, it is v velocity. When j is equal to 3, it is w velocity. Is equal to rho g z minus partial p by partial z plus mu into partial square. Now because I is equal to 3, ui would become partial w upon partial x square plus partial square w upon partial y square it would be in bracket plus partial k w upon partial left square. So we can very easily get these values. And similarly, the continuity equation, which was written in very tedious form, if I there is a certain lag. So I can for the continuity equation I can just write partial u I upon partial x I is equal to 0. So that would be suffice to say that if I expand it for the 3D, when I is equal to 1, I can write partial u upon, and x1 is partial x plus when I is equal to 2, when it, because we are going to be doing the summation, because now I is the repeating index. I can also write j here, it doesn't matter because it is a dummy variable, it is repeating variable. So partial v upon partial y plus partial w upon partial z is equal to 0. So this is your continuity equation for incompressible steady flow. So we can only represent it with one with one, what do you call, one term. And similarly, the stresses I have shown you there, like tau ij, we can write it tau ij mu into partial u I upon partial xj plus partial uj upon partial xi. Right? So if we are talking about tau xy, then because x represents 1, so I would be equal to 1 and y mean j is equal to 2. So if we put that here, that is y and this is x. So tau xy is basically equal to mu into partial u upon partial y plus partial v upon partial x. Similarly, we can write jk. In that case, j would be equal to y and k would be equal to 3, which is equal to z. So in this way, we can easily, these three relations are the tensor form. One this, and then the bit which I have shown, where this one. So these are the Navier-Stokes equation in tensor form. So if we remember only one equation, this one, we can derive all these three equations by using the tensor form of the Navier-Stokes equation, which is the last bullet point on the lecture slide. So it is not given in your book, but I thought that usually students find it difficult that how to memorize all these cumbersome equations. So there is no need to memorize all these equations. If we just know the tensor form of the equation, we can get to the component form by using the expansion as I have explained. Now, if there is any query, you can ask. Okay, so it means that everything is good. So let's do a quick numerical and then we can move forward. So in this numerical problem, we have got the two-dimensional velocity field for an incompressible Newtonian fluid is described by velocity vector is given. It means that the I component is u and j component is v. Where the velocity has unit of meter per second, that is understandable, and x and y are in meters. Determine the stresses sigma xx, sigma yy, and tau xy at the point x is equal to 0.5 meter and y is equal to 1 meter. If the pressure at that point is 6 kPa and dynamic viscosity of the fluid is 1.50 Newton second per meter square. So let me copy that relation here and then we can do something. So So somehow it is not being tuned at the moment. So let me see that. Okay. So okay, so this is the velocity velocity vector. So from here, if we know that we can get the u velocity component and v velocity component very easily. So u velocity component is 12xy square minus 6x cube, and then v velocity component, which is the velocity in the y direction, we can write it 18x square y minus 4y cube. Now we need to find sigma xx, sigma yy, and tau xy. Tau yx or tau xy, there would be the same thing for the two-dimensional flow. So first of all, if you remember that what is the relation for sigma xx and sigma yy, so then it would be easier for us to move forward. So let me write that. So sigma xx is equal to minus p plus 2 mu into partial u by partial x, and then sigma yy is equal to minus p plus 2 mu into partial b by partial y, and similarly tau xy is equal to mu into partial partial u upon partial y plus partial v upon partial x. So it means that we need these four derivatives: partial u by partial x, partial v by partial y, and these two other gradients. So if we try to calculate them here, so partial u by partial x would be equal to, if I try to write it, it would be equal to partial u by partial x would be 12y square minus 18x square, and then partial v by partial y would be equal to 18x square minus 12y square, then partial u by partial y would be equal to 24xy, and then partial v by partial x would be equal to 36 xy. Right. So now, because in the problem statement they have said that we need to put x is equal to 0.5 meter and y is equal to 1 meter, and then pressure value is also given, that is 6,000 Pascal. So if we try to put the values, so that x is equal to 0.5 meter and y is equal to 1 meter, then we can easily get the value here. So if I can write down the value, so it would be equal to sigma xx would be equal to, because it was minus 6,000 plus 2 into 1.5, which is mu value, and then partial u by partial x at y is equal to 1 and x is equal to 0.5. So that is the value is 7. It is 7.5. So if we get that value, so that is minus 5.98 kilopascal. Similarly, if we put in the values for sigma yy, that comes out to be minus 6.02 kilopascal, and then tau xy, that comes out to be 45.0 Pascal. Okay. Now tell me that how to show it these stresses on a cube, on a two-dimensional element. If we want to show it on a two-dimensional element, if we have got this two-dimensional square element. Now sigma xx value is minus 5.98, and minus means that it is not a tensile stress, but it is compressive stress. So it means that it would be something like this, minus 5.98 kilopascal. So it is kind of telling us that pressure component is quite dominant in this rather than the other stress component. And then for the sigma yy, that is minus 6.02, it is again compressive stress. That would be minus 6.02 kilopascal and minus 6.02 kilopascal. Right. And then here, how to show tau xy? Tau xy, or it is equal to tau yx. Both are the same thing. So first of all, if we talk about tau yx, if I am showing it on this plane, tau yx, the arrow should be upward or downward, anyone? Because we know that in order to be a stress to be positive, then the direction outward normal should be positive, which is this direction, and the direction on which it is pointing, that also should be positive. So if we talk about tau xy, x is the direction of the unit normal, which is positive. So y should also be positive here, like this, because the value is 45.0 Pascal. So this is 45.0 Pascal, and on this plane, if we want to show it, it would be something 45 point. It would be downward. Why it is downward? Because here the unit normal outward is negative. So in order, because this is positive value, so it should be downward. Then negative into negative would be positive. Similarly, if we want to show tau yx on this plane, the direction would be this, because this is unit normal outward in the y direction in the positive y, and here the x is also positive, so it would be 45.0 Pascal, and then here it would be 45.0 Pascal, negative in the negative direction. So I hope that you understand that the notation which we discussed, I think somewhere in the last lecture, this one. Now you are clear that how to show the direction of stresses on a plane once we calculate the values from a numerical, right? If it is positive, then it should be showing us the positive one. Otherwise, if it is negative, which is the case for the stresses which are shown here, so it should be negative. Okay. So, is there any question, any query in this bit, and the numerical bit which we covered? Okay, so it seems that you are getting everything somehow which I am teaching, so that's always good. So now, in order, if we have got any flow, any practical flow or any flow for that matter, we need, and that flow is incompressible, then we need to solve these sets of equations. Now you can see that they are non-linear equations, second order equations, so their direct solution is not possible, because our mathematics advancement hasn't got to that stage where we can solve non-linear unsteady equation by using some analytic method. So it means that whether we do some experiments to see the values of which we want to find out, or second thing we can do is that we can simplify these equations if the flow is very simple. Flow simple means that simple flow example, like if it is steady flow, that is one simplification, that there is no change in during the time. And what else? Any simplification you can think of? If it is a laminar flow means streamline flow, there is no turbulence, so that is another simplification. The third simplification means if it is kind of a one-dimensional flow. So it means that only gradient in one direction are important. Then our governing equation can be reduced to ordinary differential equation. Rather than this partial differential equation, it can be reduced to ordinary differential equation. So that those are the cases which we are going to discuss in this class. So first of that cases where the exact solution of the Navier-Stokes equation is possible, that is the steady laminar flow between fixed parallel plates, and we call it Poisson flow. Right? So we have got two infinite plates. Infinite means that they are infinite in x and infinite out of the board, and the only variation is along the y-axis, and the flow is happening in the x direction.
हाँ पे अच्छा
Yes.
आपसे उधर से अच्छा
तो ये सीन में जाता है
सही तो फिर वो क्या मतलब
अस्सलाम
क्या सीन है आगे से टूर का कहाँ जा
अस्सलाम
रहे थे
मैं जा रहा हूँ
अस्सलाम, can you
एक
hear
हफ्ता
me?
हो गया बस एक हफ्ता
जुम्मे के
हो गया
बाद हूँ
Hassan, are you there? Hassan Mustafa.
Yes, sir.
Can you please convey this message to Arslan and all those who want to communicate at their for their personal reasons? Please don't use this forum for that. Okay? Please communicate at your own time. Okay, so I was talking about the exact solution for the Navier-Stokes equation, the flow situation where we can have the exact solution. So that the first case is the steady laminar flow between fixed parallel plates. That is called Poisson flow. So in this, there is no variation in the flow velocity in the x direction. There is only variation of velocity in the y direction, but the flow is happening in the x direction. Mind it, the flow is occurring in the x direction, but because the flow is fully developed, it means that along a streamline there is no gradient. So it means that there is only variation in y direction. So that flow is called Poisson flow. So that is the flow which occurs when we have got two parallel plates and we are trying to get some flow happening in between those two plates. And then it is kind of you can say a simplified form of duct flow. And then the second one is Poisson flow, in which we have got the one plate is moving and one plate is stationary, but the flow is happening in only in x direction. So it means that at the lower plate the velocity would be zero, at the upper plate the velocity would have some uniform value. So the practical example of this is the flow of some oil or grease in that ball bearing. So that is that, because in that ball bearing the upper bit is moving. So that is circular, but we can always break it and pan it out in form of this flat plate, right? And then we have got steady laminar flow in circular tube, and then steady axial laminar flow in annular. Annular means that we have got two concentric pipes, and there is a flow between the space between the outer pipe and inner pipe, right? So we are going to start the that how to get the solution for the Navier-Stokes equation for the steady laminar flow between fixed parallel plates, and then we would finish that discussion in the next class, hopefully. So now we are going to consider steady laminar flow between fixed parallel plates. So this type of flow is called Poisson flow. So the scientists which gave the solution for this type of flow, his name was Poisson, so that's why we call it Poisson flow. So we would only go through the assumptions here, and the rest of the solution we would do in the next class. So let me zoom it a little bit. Yes, any question? Ji Assam? Assam, anything you want to add? Maybe not. Okay, so if you look here, that we, first of all, the coordinates are defined at the center. It means because this type of flow is symmetric around this central axis, so that is the plane of symmetry, the center line. And if you see that x-axis, y-axis here starts from the center of the plate, and y would be equal to 0 here, and it would be h here height and minus h on the lower side. Now, if we look at the assumption for this type of flow, so that is the first assumption that the plates are infinite and parallel plates. Infinite in x and z direction. That is the out of the board plane. So that is the first assumption. The flow is steady. That's true. And then laminar, which means streamline flow. There is no turbulent fluctuation in that. Now, fluid flow in the x direction only, it means that fluid is only flowing in the x direction, so v velocity component and w velocity component and are 0, and u is only function of y. U is not changing in x, so it means that it is fully developed. So for the fully developed flow, we say that partial u by partial u by partial x is equal to 0. So if that is the condition, that is called fully developed flow. It means that the flow properties are not changing in x direction. So any direction in which we say that it is fully developed, it means that the flow velocities remain constant in that direction. So it is not going to change if we extend that length. So that is the assumption. And then the fifth assumption, it is incompressible. And the governing equation which we need to okay, so we would simplify these equations in the next class, and I have done some kind of simplification showing. If you see that I have put some number in where I kind of cancelled out the term, so 1 2 3 4 5, so these numbers which are written here, they correspond to the cancellation of the term during due to that assumption. So I hope we would take it from there, from this point, that what is mean by 2 mean here that the flow is steady, so the time dependent term is 0. 4 means that fully developed, so partial u by partial x is equal to 0. Then 3 mean that v is equal to 0, so that's why I have put here v is equal to 0, and the rest of the terms I would explain in the next class. So if there is any query, you can ask, otherwise we can finish the lecture for today. So let me download